Tonight, we're going to explore a quiet misconception, one so deeply embedded in how most of us picture space travel that we rarely stop to question it. The idea that flying to another planet is simply a matter of pointing a rocket in the right direction and pressing go. Here's a strange, almost paradoxical fact to start with. To reach the Sun, the single largest, most massive object in our entire solar system, sitting at the center of everything, its gravity dominating every planet, every asteroid, every speck of dust for billions of kilometers in every direction. A spacecraft launched from Earth must first hit the brakes. Hard. It has to shed a staggering 67,000 miles per hour of its own sideways motion. If it doesn't, it won't fall into the Sun at all. It will simply miss it and settle into a new, permanent orbit around it, forever, exactly the way Earth itself does. It is, by the actual mathematics involved, considerably harder to hit the Sun than it is to leave the solar system entirely. If that sounds backward, you're not alone in finding it strange. It runs directly against nearly every intuition Earth ever taught us about how to get somewhere. For decades, popular imagination has treated interplanetary travel as a scaled-up version of ordinary terrestrial movement. Point yourself at the destination, apply power, arrive. Astronauts and engineers, working through the actual physics involved, have known for over half a century that this picture is almost entirely wrong. The first surprise is that you cannot fly to another planet in a straight line, ever, under any circumstances. The physics of orbital motion simply forbids it. The second is that even after solving that problem, the sheer mathematics of rocket fuel imposes a kind of tax so severe that the actual cargo delivered to another world is often less than 2% of what left the launch pad. And the third, the part this entire documentary is really about, is what happens after a spacecraft survives the journey and finally arrives. A gauntlet of radiation, abrasive dust, brutal temperature swings, and a communication delay so long that no human being anywhere can actually fly the spacecraft during the single most dangerous minutes of its entire mission. Here's something worth knowing before we go any further. Nearly everything in tonight's story is drawn from missions that have actually flown, actually failed, or actually succeeded. Real engineering, tested against the full, unforgiving weight of physical reality, not speculation about some distant, hypothetical future. Every number, every near miss, every quiet triumph belongs to a specific spacecraft, built by a specific team who staked years of their working lives on getting the mathematics exactly right. By the end of tonight, you're going to understand exactly why interplanetary travel remains one of the most mathematically punishing, engineering-intensive undertakings our species has ever attempted. And why, after 60 years of hard-won lessons, we may finally be standing at the edge of genuinely solving it. Let yourself settle in. There's no need to hold every number precisely tonight. Just let the shape of the difficulty and the slow, patient story of overcoming it wash over you. Here is where tonight's journey will take us. We'll begin by dismantling the comforting illusion of easy space travel, discovering why a spacecraft can never simply point itself at a planet and go, and what it actually takes to hit a moving target across an emptiness large enough to swallow every intuition Earth ever gave us. We'll sit with the punishing mathematics of the rocket equation and understand why the overwhelming majority of every rocket ever launched is, in the end, nothing more than fuel built to carry more fuel. We'll walk through two of the most extreme, opposite engineering nightmares in the solar system. Venus, a crushing, furnace-hot death trap, and Mars, a world with just enough atmosphere to kill you and not nearly enough to save you. We'll meet the invisible enemies waiting on every planetary surface. Cosmic radiation quietly flipping the ones and zeros inside a spacecraft's own computer. Abrasive dust grinding away at seals and solar panels, and temperature swings violent enough to crack steel. We'll confront the tyranny of light speed delay and understand why no human being has ever truly driven a rover on another world in real time. We'll revisit some of the most heartbreaking failures in the history of interplanetary exploration. Missions lost not to some grand cosmic catastrophe, but to a single misplaced decimal point, a single second of bad data. And we'll end, as we always do, by turning this back toward what it means that a species this fragile, on a planet this comparatively comfortable, keeps choosing, deliberately, to hurl its own machines into an environment that wants nothing more than to destroy them. Before we dive in, if the quiet, patient engineering behind humanity's reach into the cosmos is the kind of thing that helps settle your mind at the end of a long day, consider liking this video or subscribing to the channel. It's a small thing. It costs you nothing. But it helps this kind of slow, patient science storytelling reach the people who need exactly this tonight. Now, let's begin. Almost everything we understand about traveling somewhere comes from a lifetime spent on the surface of a single planet. And that lifetime of intuition turns out to be almost entirely useless once you leave it. On Earth, movement follows a simple, familiar logic. You point yourself at your destination and you apply continuous power to overcome friction and gravity until you arrive. A car fights the friction of the road. A plane fights the drag of the air. Stop applying power, and you stop moving, more or less immediately. This is the only kind of travel most human beings have ever personally experienced, and it shapes, almost invisibly, how we imagine every other kind of travel too, including travel between planets. In the frictionless emptiness of space, that entire intuition collapses. There is no road to grip, no air to push against, and critically, nothing bringing a spacecraft gently to a stop once its engines shut off. But the deeper problem isn't the absence of friction. It's something stranger and far less intuitive. Nothing in space is actually standing still, waiting to be reached. Every planet in our solar system, including the one you're lying on right now, is in constant, rapid motion, orbiting the sun at tens of thousands of kilometers per hour, tracing out a vast, unending ellipse that never once pauses to let anything catch up to it. A spacecraft aimed at Mars isn't aimed at where Mars currently sits. It's aimed at a specific, empty point in space where Mars will be, months from now, after a journey that hasn't even begun yet. A mathematical bet placed months in advance on the future position of a moving target hundreds of millions of kilometers away. Here's a way to feel this, rather than simply hear it described. Imagine standing on the edge of a rapidly spinning merry-go-round, trying to throw a ball to a friend standing perfectly still at its center. The ball doesn't travel in a straight line toward your friend at all. The instant it leaves your hand, it inherits the sideways, rotational speed of the platform you were standing on, curving wildly away from where you actually aimed it, exactly the way a spacecraft launched from Earth inherits Earth's own staggering sideways motion around the sun. And Earth's sideways motion is not a small detail to inherit. To simply maintain its own orbit and avoid spiraling either into the sun or drifting off into deep space, Earth travels at an average of just under 30 kilometers per second, roughly 107,000 kilometers per hour. Every spacecraft ever launched from Earth's surface carries that exact same staggering velocity with it, automatically, the instant it leaves the ground, whether the mission planners want it or not. This single fact reshapes everything about how interplanetary missions actually work. A spacecraft cannot simply point its nose at Venus or Jupiter or anywhere else and fire its engines toward the target. To visit the inner solar system, somewhere like Venus or Mercury, closer to the Sun than Earth, a spacecraft actually has to fire its engines backward against the direction of Earth's own orbital motion, deliberately shedding some of that inherited 30 kilometers per second velocity. Slower than before, it can no longer maintain its orbital distance, and it begins falling inward toward the Sun, picking up speed as it descends deeper into the Sun's gravity well. To visit the outer solar system instead, somewhere like Mars or Jupiter, the spacecraft does the opposite, firing its engines in the same direction as Earth's orbit, adding to that inherited velocity which pushes its orbit wider out and away from the Sun. Because sustained, continuous rocket power simply isn't achievable with current chemical propulsion. There isn't remotely enough fuel to burn engines the entire way. Engineers instead rely on something called a Hohmann transfer orbit. It works like this. A single, brief, intense engine burn nudges the spacecraft onto a long, curving elliptical path, carefully calculated so that this path intersects the target planet's own orbit at precisely the moment the planet itself arrives at that same point in space. After that one initial burn, the spacecraft's engines fall almost entirely silent. It simply coasts, unpowered, for months, sometimes years, trusting the mathematics laid down at the very start of the journey to bring it, eventually, to the correct place at the correct time. If that timing is off by even a fraction of a degree at departure, the consequences compound catastrophically across the following months. The spacecraft doesn't crash. It doesn't explode. It simply arrives at the calculated intersection point precisely on schedule, only to find that the planet itself isn't there, having been ever so slightly miscalculated, leaving the spacecraft alone, coasting silently through a targetless patch of empty space, continuing its own lonely orbit around the Sun indefinitely, forever. There's a genuinely strange consequence hidden inside all of this, worth sitting with before we move on. Escaping the solar system entirely, breaking free of the Sun's gravity forever, sailing outward past every planet, never to return, requires adding roughly 12 kilometers per second of velocity to a spacecraft leaving Earth. Crashing directly into the Sun, by contrast, requires cancelling out almost the entirety of Earth's own 30 kilometers per second orbital velocity. It is, in very real, mathematically precise terms, considerably harder and considerably more energy expensive to hit the Sun than it is to leave the solar system behind forever. The largest, most gravitationally dominant object in our entire cosmic neighbourhood is, paradoxically, one of the hardest targets in it to actually strike. A short pause here, if you'd like one. Nothing in tonight's story requires you to hold every number precisely. Just the shape of it, a solar system that never holds still, and a physics that rewards patience over force. Let your shoulders soften, and we'll continue. Before we go further, it's worth sitting with the actual distances involved. Not as abstract numbers, but as something closer to felt scale, because these distances dictate the entire architecture of every mission ever flown. Venus, our nearest planetary neighbour, sits anywhere between 38 million and 261 million kilometres from Earth, depending on where each planet happens to be in its own orbit at any given moment. At its closest, sunlight reflected off Venus takes just over 2 minutes to reach us. At its farthest, that same light takes nearly 15 minutes. Mars, our other close neighbour, and by far the most popular target for exploration, ranges from about 55 million kilometres away at its closest to just over 400 million kilometres at its farthest. A journey that light itself takes anywhere from 3 minutes to a genuinely startling 22 minutes to complete. And Jupiter, the first of the outer giants, sits somewhere between roughly 588 million and 968 million kilometres away. Distant enough that light alone takes between 35 and 52 minutes just to make the one-way crossing. Here's what makes these numbers especially strange to sit with. They aren't fixed. Because every planet moves along its own elliptical path, at its own particular speed, the actual gulf between any two worlds is constantly expanding and contracting, opening and closing narrow, temporary windows during which a journey between them becomes mathematically efficient at all. Miss that window, and a mission might have to wait months, or in some cases years, for the next one to open. This is a detail that surprises most people the first time they really sit with it. Mars launch windows, for instance, open only roughly once every 26 months. The specific interval it takes for Earth and Mars, moving at their own different orbital speeds, to return to a favourable alignment relative to each other. Miss a launch window by even a matter of weeks, and the next viable opportunity to launch isn't simply a little later, it's over 2 years away. Entire missions, representing years of design work and enormous budgets, have their launch dates fixed years in advance, built around a narrow, unforgiving calendar dictated entirely by the orbital mechanics of 2 planets that, quite simply, do not care about anyone's schedule but their own. There's a simple way to feel just how enormous even our closest planetary neighbour actually is. At its closest possible approach, Mars sits roughly 4,000 times farther from Earth than New York is from Sydney, Australia. Already one of the longest direct flights human beings ever routinely take. If you shrank Earth down to the size of a basketball, Mars, at that same reduced scale, would be a softball, sitting a full 10 miles away. And even this staggering distance is only the beginning of the story, because nothing in space stays still. And because the fuel available to actually chase down a moving target is agonizingly limited, every one of these vast distances has to be crossed using precisely the kind of careful, patient, mathematically punishing strategy we explored in the last chapter. Never a straight line, never a direct shot, always a long, curving, carefully timed arc across an abyss that refuses to hold still. If the geometry of orbital mechanics is the first great obstacle standing between us and other worlds, the second is something even more unforgiving. A single piece of mathematics worked out over a century ago by a Russian schoolteacher named Konstantin Tsiolkovsky that governs every rocket ever built, with absolutely no exceptions. There's something worth appreciating about the origin of this particular piece of mathematics before we get to what it actually says. Tsiolkovsky worked largely in isolation, deep in provincial Russia, partially deaf since childhood, supporting himself as a schoolteacher while working out the fundamental physics of rocketry almost entirely through his own independent reasoning, decades before any rocket capable of reaching space actually existed. He published his key equation in 1903, the same year the Wright brothers achieved their first powered flight, a full 54 years before humanity would launch anything into orbit at all. He never saw a single spacecraft built using his own equation, and yet every single rocket ever launched since, without exception, has had to obey the exact relationship he worked out, alone, with nothing but mathematics and imagination, at the turn of the 20th century. The relationship is elegant and genuinely punishing. It connects how much a rocket's velocity can change to the exhaust speed of its engines and to the ratio between its initial mass, fuel included, and its final mass once that fuel has been burned away. Buried inside that relationship is a natural logarithm. And logarithms, in this particular application, create something engineers sometimes describe, only half-jokingly, as an exponential tyranny. To increase a rocket's speed by a fixed, linear amount, you don't need a proportionally larger amount of fuel. You need an exponentially larger amount. And because fuel itself has weight, adding more of it doesn't just add cargo. It adds a burden that then requires still more fuel, just to lift the fuel you already added off the launch pad in the first place. Here's a way to actually feel this, rather than just hear the mathematics described. Imagine planning a very long road trip across a vast, uninhabited desert, with no gas stations anywhere along the route. Every drop of fuel the entire journey will ever need has to be loaded into your vehicle before you leave, but that fuel itself weighs a great deal. So now your car needs a bigger engine just to move all that added weight, which burns fuel faster, which means you need to carry even more fuel to compensate, which adds still more weight. By the time you've accounted for the entire journey, you're no longer driving a car at all. You're driving a colossal tanker truck built almost entirely to deliver a single passenger and a small suitcase to a destination far across the sand. This is not a rough analogy. It is, essentially, exactly what a rocket is. The Saturn V rocket, the largest, most powerful vehicle ever built to carry human beings, weighed just under 3 million kilograms sitting on the launch pad. Of that entire mass, the size of a naval destroyer, standing on end. The actual payload it delivered toward the moon amounted to only about 48,600 kilograms. That works out to a payload fraction of roughly 1.64%. 98.5% of the largest rocket humanity has ever launched was, in the end, nothing more than fuel, and the structure needed to hold that fuel, built entirely in service of delivering a comparatively tiny fraction of cargo to its destination. Modern rockets haven't escaped this same brutal ratio. SpaceX's workhorse Falcon 9, one of the most successful, most frequently flown rockets in history, manages a payload fraction of only around 4% to low Earth orbit. Better than the Saturn V, genuinely, but still a world away from anything resembling efficiency by ordinary terrestrial standards. Across essentially every launch vehicle ever built, the actual structural mass, the metal, the engines, the guidance computers, everything that isn't simply propellant, typically accounts for a mere 5 to 10% of the vehicle's total weight at launch. The overwhelming remainder is explosive fuel, waiting to be burned, second by second, just to escape the modest pull of Earth's own comparatively gentle gravity. Because fuel is this precious, this scarce, once a spacecraft is actually in space, its engines fall almost completely silent for the majority of any interplanetary journey. A typical mission to Mars, for instance, involves a single, violent, tightly choreographed engine burn lasting only a handful of minutes. And then, for the following 9 months, the spacecraft simply coasts, unpowered, trusting entirely in the trajectory calculated back at the very start of the trip. And that trust carries enormous, unforgiving precision requirements, because interplanetary paths are effectively long, sweeping arcs traced across hundreds of millions of kilometers. Even the smallest initial error compounds dramatically over time. A velocity mistake of just 1 meter per second at the very start of a journey, roughly an ordinary human walking pace, can, over the course of a 200-day transit to Mars, alter the spacecraft's farthest orbital point by tens of thousands of kilometers, and ultimately produce an arrival missed distance of over 4,500 kilometers from the intended target. To correct for these slow, accumulating drifts, engineers schedule small, carefully calculated trajectory correction maneuvers along the way. Brief, precise engine firings meant to nudge the spacecraft back onto its intended path. But the fuel reserved for these corrections is itself strictly, unforgivingly limited, leaving essentially no margin for a mistake large enough to require more than a handful of these gentle nudges across an entire journey. Surviving the journey itself, remarkable as it is, only gets a spacecraft halfway to its goal. Arriving at another world is not the same thing as landing on it safely. And 2 of our nearest planetary neighbours, Venus and Mars, present what amount to 2 entirely opposite engineering nightmares, each one demanding a radically different survival strategy. Let's start with Venus, sometimes called Earth's twin for its similar size. A comparison that stops being flattering almost immediately once you look closer. Venus possesses an atmosphere roughly 92 times thicker than our own, producing a surface pressure equivalent to being submerged nearly a kilometre underwater in Earth's own oceans. Its surface temperature holds steady, day and night, at a punishing 460 degrees Celsius. Hot enough, easily, to melt lead, and more than sufficient to destroy ordinary electronics within moments of exposure. There is, notably, no meaningful difference between day and night on the Venusian surface at all. The atmosphere is so thick and circulates heat so efficiently across the entire planet that the temperature barely varies whether you're standing in full sunlight or on the planet's darkened far side, a detail that makes Venus feel less like a planet with weather and more like a single planet-wide furnace, sealed shut and left running permanently at full temperature. Entering that atmosphere is its own violent ordeal. Plasma temperatures during descent peak above 2,000 degrees Celsius as the thick atmosphere tears at any spacecraft attempting to pass through it. But here's the genuinely counterintuitive part. On Venus, Slowing down isn't actually the hard part. That same thick, punishing atmosphere acts as an enormously effective natural brake, doing much of the deceleration work almost for free. The real challenge on Venus isn't surviving the descent. It's surviving what waits at the bottom. During the Soviet Union's Venera program, spanning the 1970s and into the 1980s, engineers built landers from solid titanium spheres, deliberately chilled them well below freezing before launch, and packed them with special phase change materials designed to slowly absorb heat from the inside, buying every possible extra minute of survival once they touched down. Despite these genuinely heroic engineering efforts, none of them lasted especially long. Venera 13, among the most successful of the entire program, functioned on the Venusian surface for 127 minutes in March of 1982, before the crushing pressure and relentless heat finally liquefied its seals and imploded its internal electronics. Here's a way to feel the sheer hostility of that environment. Landing on Venus is, in essence, like dropping a fully functioning computer into a deep fryer set to full temperature at the very bottom of the Mariana Trench, the deepest point in all of Earth's oceans, and hoping it manages to keep working anyway for even a couple of hours. Mars presents almost the exact opposite problem in nearly every respect. Its atmosphere is roughly 100 times thinner than Earth's own, thick enough to generate serious, genuine heating during entry, with temperatures peaking around 1500 degrees Celsius, but nowhere near thick enough to actually slow a heavy spacecraft down safely using parachutes alone, the way a similar mission might manage on Earth. Mars, in other words, offers just enough atmosphere to threaten a spacecraft with real danger, and nowhere near enough atmosphere to offer any real protection from it. Engineers frequently, only half-jokingly, call it the hardest place in the entire solar system to actually land on. For heavy, one-ton scientific rovers, vehicles like Curiosity and Perseverance. This contradiction forces engineers into one of the most complex, entirely automated sequences ever devised for any spacecraft, anywhere. It has earned, among the people who build and fly it, a genuinely fitting nickname, the 7 Minutes of Terror. And it deserves its own chapter, entirely on its own, because there is nowhere else in tonight's story where quite so much can go wrong, quite so quickly, with absolutely no possibility of human intervention at any point along the way. Let's walk through this sequence slowly, moment by moment, because it's genuinely one of the most remarkable feats of autonomous engineering our species has ever accomplished. And because understanding exactly how much has to go right in exactly how little time is the only way to appreciate exactly how much can go wrong. The sequence begins the instant a spacecraft first touches the outer edge of the Martian atmosphere, traveling at a punishing 20,000 kilometers per hour, roughly 100 kilometers above the surface. Almost immediately, atmospheric friction begins generating extreme heat, and the spacecraft's protective shield takes the full brunt of it. By roughly 80 seconds into the descent, the spacecraft reaches peak heating. Its ablative heat shield, a layer specifically designed to burn away, absorbing and carrying off heat as it does, enduring temperatures around 1500 degrees Celsius, while the vehicle has already slowed dramatically, down to around 1600 kilometers per hour. At roughly the 240-second mark, still traveling faster than the speed of sound, a massive parachute, 21.5 meters across, is fired explosively out of a mortar-like launch tube, deploying while the spacecraft is still moving at nearly twice the speed of sound. 20 seconds later, with the vehicle now finally subsonic, the heat shield itself, having done its job, is jettisoned entirely, exposing radar and specialized cameras that begin scanning the ground below for the very first time, comparing what they see against preloaded maps to determine, with real precision, exactly where the spacecraft actually is. By roughly the 350th second, the parachute alone simply isn't enough anymore. For a vehicle weighing a full metric ton, like Curiosity or Perseverance, that parachute can only slow things so far, down to around 320 kilometers per hour, at an altitude of just over 2 kilometers. At that point, the spacecraft cuts itself free from the parachute entirely and ignites a set of retro rockets, steering itself deliberately away from the discarded parachute and backshell to avoid any risk of collision. And then comes the single strangest, most audacious part of the entire sequence. Something engineers call the sky crane maneuver, because firing rocket engines directly at the Martian surface would kick up a violent cloud of dust and debris, potentially damaging the delicate rover itself. The descent stage instead comes to a hover roughly 20 meters above the ground and gently lowers the rover down on a set of nylon cables, like a spider lowering itself on its own silk. Only once the rover senses its own weight resting fully on its wheels does the descent stage sever those cables with small explosive charges and fly itself away, deliberately crashing at a safe distance to avoid coming down anywhere near the rover it just delivered. A brief pause here, if you'd like one. Picture that image for a moment. A spacecraft hovering, patiently, 20 meters above an alien surface, lowering its precious cargo on cables entirely alone. There's something quietly beautiful in that, even amid all this tension. We'll continue when you're ready. From first atmospheric contact to a fully successful touchdown, the entire sequence takes right around 7 minutes. And here is the detail that turns this from merely difficult into something genuinely nerve-wracking for every engineer watching from Earth. Because the one-way communication delay to Mars typically runs somewhere between 11 and 14 minutes, every single one of these steps. The parachute deployment, the heat shield separation, the retro rocket ignition, the sky crane's delicate, cable-lowered touchdown, has to happen entirely on its own, without any possibility of human guidance, correction, or intervention at any point. By the time Mission Control on Earth even receives the very first signal confirming that the spacecraft has begun entering the atmosphere, the entire 7-minute sequence has already finished, one way or another. The rover is already sitting safely on the Martian surface, sending back its first triumphant images, or it has already been destroyed, a scattered debris field on the Martian dust, its mission over before anyone on Earth even knew it had truly begun. There is no version of this sequence where a human being, watching anxiously from a control room hundreds of millions of kilometers away, could have stepped in to help. Every single decision, every correction, every split-second response to unexpected data has to be made entirely by the spacecraft itself, trusting software written years in advance by engineers who will never know, in real time, whether their work succeeded or failed. This particular stretch of every Mars landing has become something close to a cultural ritual in its own right among the engineers who live through it. Inside Mission Control at NASA's Jet Propulsion Laboratory, entire rooms of scientists and engineers, some of whom have spent the better part of a decade on a single mission, sit together during those 7 minutes, watching a screen that can only confirm, after the fact, whether the sequence already succeeded or failed, minutes earlier, hundreds of millions of kilometers away. There is nothing for anyone in that room to actually do during those 7 minutes except wait. A peculiar, modern form of powerlessness, watching the culmination of years of work unfold in complete silence, already decided, long before the confirmation signal even begins its own lonely journey back across the solar system. Surviving the journey and surviving the landing still isn't the end of the gauntlet. Once a spacecraft finally sits on the surface of another world, an entirely different, quieter, far more insidious set of threats begins working against it. Invisible enemies that never announce themselves and that most people never think to consider at all. The first of these is cosmic radiation, beyond the protective boundary of Earth's own magnetic field. The same invisible shield that keeps you safe every single day without you ever noticing it's there. The solar system is bathed in a constant, relentless flux of high-energy particles arriving from the sun and from far beyond our own solar system entirely, sweeping in from deep space at extraordinary speeds. When one of these high-energy particles happens to strike a silicon microchip inside a spacecraft's own onboard computer, It can deposit just enough localized electrical charge to physically flip a single digital bit, turning a stored 0 into a 1 or a 1 into a 0, essentially at random. Engineers call this a single event upset, and the consequences can range from utterly harmless to genuinely catastrophic, depending entirely on which specific line of code, out of millions, happens to be struck at that exact unlucky moment. A flipped bit in the wrong place, at the wrong time, can trigger an unplanned system reboot in the middle of a critical maneuver. Precisely the kind of failure that offers no warning and no possibility of correction from hundreds of millions of kilometers away. To defend against this invisible threat, spacecraft cannot simply use the same consumer-grade processors found in an ordinary smartphone or laptop. Instead, engineers rely on specially manufactured radiation-hardened chips, built using specific transistor designs engineered specifically to resist this kind of random electrical disruption, and a redundancy technique called triple modular redundancy, where 3 entirely separate logic circuits perform the exact same calculation simultaneously in parallel. If a stray particle happens to flip a bit in one of the 3, corrupting its result, the system simply takes a majority vote among all 3 circuits, silently, automatically discarding the corrupted answer and continuing on as though nothing had happened at all. This kind of protection comes at a genuinely staggering cost. The primary processor used aboard NASA's most advanced Mars rovers, a chip called the RAD750, runs at a maximum clock speed of just 200 MHz, a small fraction of the raw processing power inside an ordinary modern smartphone, and costs upwards of $200,000 per individual unit. By any consumer standard, it is almost absurdly slow and almost absurdly expensive. But it can withstand a cumulative radiation dose of up to 1 million rads of total ionizing exposure. A dose so extreme that a mere 400 to 500 rads would be lethal to an unprotected human being. The RAD750 isn't slow because engineers couldn't build it faster. It's slow because every single design choice was made in service of one overriding priority: surviving an environment that would reduce an ordinary consumer processor to slag within minutes. There's a genuine trade-off worth sitting with here, one that runs through nearly every piece of spacecraft engineering discussed tonight. A faster, more capable consumer-grade processor would let a rover think faster, process images more quickly, make more sophisticated autonomous decisions in real time. But that same processor, unprotected against radiation, might survive only days or even hours before a single unlucky particle strike corrupted its memory beyond recovery. Engineers, faced with that trade-off, consistently choose reliability over raw speed. A slower brain that reliably works over a faster one that might fail catastrophically at exactly the wrong moment, with nobody able to reach out across 100 million kilometers and simply restart it. This same invisible threat poses an even more serious danger to human crews rather than machines. NASA maintains a strict career radiation exposure limit of roughly 600 millisieverts, specifically designed to keep the lifetime increase in cancer risk within an acceptable bound. A standard 9-month chemical propulsion transit to Mars pushes astronauts dangerously close to, or in some mission profiles beyond, that entire career limit in the span of a single round trip. A sobering reality that, as we'll discuss later tonight, is quietly reshaping how engineers think about the propulsion systems of the future. The second invisible enemy waiting on a planetary surface is something that sounds, at first, almost mundane: dust. It is anything but. Planetary regolith. The loose surface material covering worlds like the Moon and Mars bears almost no resemblance to ordinary terrestrial dirt. On Earth, dust and soil are worn smooth over countless centuries by the constant, patient action of water and wind, rounding off their sharp edges the way a river smooths a stone. On worlds without that same erosion, regolith particles remain exactly as jagged and sharp as the moment they were first created, often through violent impacts. microscopic shards, some barely a few micrometers across, closer in structure to shattered glass than to soil. Many of these particles carry a static electric charge as well, causing them to cling stubbornly to camera lenses, to solar panels, to any exposed mechanical joint, slowly degrading optical clarity and grinding away at seals and moving parts with a persistence no amount of careful engineering can entirely design around. Dust doesn't just create a nuisance. It directly dictates how long a mission can survive. In 2018, a massive, planet-wide dust storm swept across Mars, blotting out the sun for months at a time. NASA's Opportunity rover, entirely dependent on solar panels for its electrical power, watched the atmosphere above it grow so thick with suspended dust that its panels could no longer generate enough energy to keep its internal heaters running. Stripped of that thermal protection, with no other power source to fall back on, the rover slowly, silently froze to death in the darkness. A mission that had already run 15 years beyond its original 90-day design lifetime, ultimately undone not by a dramatic malfunction, but by the simple, patient accumulation of dust in the Martian sky. There's something quietly moving in how that particular mission actually ended. Engineers on Earth continued sending wake-up commands to Opportunity for months after the storm began, hoping against hope that enough sunlight might eventually break through the settling dust to recharge its batteries. The rover's very last transmission, received before the silence became permanent, reported a dwindling battery level and an ominously darkening sky. A machine faithfully reporting its own decline, right up until it simply couldn't report anything at all anymore. It remains, for many of the engineers who worked on it, one of the more emotionally difficult endings in the entire history of planetary exploration. Not a sudden catastrophe, but a slow, patient fading, entirely outside anyone's control on a distant world where no human hand could ever reach out to help. That brings us to the third invisible enemy, temperature itself, and the strange, paradoxical way it behaves in a vacuum. On Earth, air constantly carries heat away from any warm object through simple convection, the same principle that makes a breeze feel cooling against your skin. In the vacuum of space, or on the surface of an atmosphere as thin as Mars's own, that convective cooling essentially disappears entirely. A spacecraft exposed to direct sunlight can absorb enormous amounts of heat, with nowhere for that heat to easily escape, while a surface facing away from the sun into the depths of space can plunge toward temperatures approaching absolute zero, all at the very same time on the very same vehicle. On the Martian surface specifically, temperatures can swing from a relatively comfortable 20 degrees Celsius during the day down to a brutal minus 130 degrees Celsius at night. A swing severe enough to freeze lubricants solid, crack delicate electronics, and turn ordinarily flexible steel dangerously brittle. To survive that kind of punishing thermal whiplash, advanced missions rely on a combination of heat pipes, adjustable louvers, and multi-layered insulation blankets, all working together to actively manage where heat flows and when. But the single most important piece of this survival puzzle, for flagship missions like Curiosity and Perseverance, is a device with a name almost as unassuming as its function is remarkable: the Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG for short. It works, at its core, almost like a nuclear battery, containing just under 5 kilograms of a radioactive isotope, plutonium-238, in the form of a dense oxide. That plutonium doesn't need to be intentionally triggered or controlled. It simply, continuously, undergoes natural radioactive decay, releasing a steady 2,000 watts of pure thermal energy, hour after hour, day after day, entirely on its own. Using solid-state components that convert heat directly into electricity, the MMRTG turns a modest fraction of that continuous heat output into about 125 watts of usable electrical power. The remaining thermal energy, far larger in quantity, is circulated directly through fluid loops woven throughout the rover's own chassis, actively keeping its most sensitive, delicate electronics warm enough to survive the lethal cold of a Martian night, regardless of dust storms, regardless of the long Martian winter, regardless of anything the environment might otherwise throw at it. Engineered to last between 14 and 17 years, powered by an isotope with a natural radioactive half-life of 87 and 7/10 years, the MMRTG requires no moving parts, no maintenance, and no attention at all, quietly generating heat and power for the entire working lifetime of the mission it serves. Here's a way to hold everything covered across these last 2 chapters together in a single image. Designing electronics to survive on another planet is a little like engineering a laptop that has to keep working flawlessly while sitting inside a microwave, set to its defrost cycle, placed inside a freezer while simultaneously being sandblasted continuously with crushed glass. Every single one of those conditions, on its own, would be a serious engineering challenge. On Mars, spacecraft face all of them, together, at once, for years at a time, with no possibility of a service call. There's one more fundamental limit, standing between Earth and every other world in the solar system, and unlike everything discussed so far, no amount of clever engineering can ever fully eliminate it, because it isn't an engineering problem at all. It's a fact about the universe itself. Light travels at roughly 300,000 kilometers every single second, by any ordinary human standard, effectively instantaneous. But across interplanetary distances, even that staggering speed becomes a genuine, meaningful delay. A radio signal, traveling at the exact same speed as light itself, takes anywhere from about 3 minutes to a full 22 minutes to reach Mars, depending on where the 2 planets currently sit in their respective orbits. To reach Jupiter, that same signal needs anywhere from 35 to over 50 minutes, one way. This delay quietly, completely eliminates any possibility of remotely piloting a spacecraft the way you might imagine flying a drone or driving a remote-controlled car. Picture a rover on the Martian surface, approaching the edge of an unseen cliff. The video feed showing that cliff, however sharp and immediate it might look on a screen back on Earth, actually left Mars up to 20 minutes ago. If engineers watching that feed immediately urgently transmit a command to stop, that command itself then needs another full 20 minutes just to physically reach the rover, traveling across the very same gulf of space. By the time the stop command finally arrives, assuming everything went exactly according to plan, the rover has already been driving, blind to any warning, for nearly 40 minutes. Trying to manually control a rover on Mars, in other words, would be something like trying to drive a remote-controlled car through a genuinely dangerous obstacle course, using nothing but a video feed delayed by a full half hour, reacting, always, to a version of events that has already changed by the time you see it, and issuing commands that won't arrive until the situation has changed yet again. A short pause here, if it helps. There's something almost meditative in this particular fact, that even our fastest possible form of communication, light itself, still isn't fast enough to erase the distance between 2 worlds. Let that settle, and we'll continue. Because of this unbridgeable delay, every rover, every lander, every deep space probe humanity has ever sent beyond Earth's immediate orbit has had to become something closer to a fully independent, self-directing robot, rather than a remotely operated machine in any conventional sense. Modern rovers rely on onboard laser scanning, stereoscopic hazard detection cameras, and sophisticated path planning software. Techniques like terrain relative navigation, which compares live camera images against preloaded orbital maps in real time, all working together to let the vehicle make its own split-second survival decisions entirely on its own, without a single moment of direct human input. This same unbreakable delay reaches its most extreme, almost dizzying scale far beyond the inner planets. When Voyager 1, humanity's most distant spacecraft, eventually crossed the threshold of 16 billion miles from Earth, a radio signal travelling at the full speed of light took a staggering 24 hours, an entire day, just to reach it, one way. A conversation with Voyager 1, at that distance, isn't a conversation at all, in any meaningful sense. It's closer to two people leaving each other letters, a full day apart, each one responding to something the other said a full day before, forever slightly, permanently out of sync. Distance in the solar system doesn't just impose a communication delay. It imposes a cost measured in something far more personal. Human careers, and in some cases, the majority of an engineer's entire working life. Because chemical propulsion simply doesn't carry enough fuel to power a direct, continuous journey to distant worlds like Mercury or Saturn, mission planners rely on an elegant, almost thrifty technique called a gravity assist, sometimes described more casually as a slingshot maneuver. By carefully approaching a planet from exactly the right angle, timed to trail slightly behind that planet's own path around the Sun, a spacecraft can effectively siphon off a small fraction of that planet's own orbital momentum, gaining real, measurable speed relative to the Sun, without spending a single additional drop of its own limited fuel. It's worth pausing on how genuinely strange this maneuver is, once you actually think through the physics of it. A gravity assist doesn't create energy from nothing. It borrows a minute, genuinely immeasurable amount of orbital momentum from an enormous planet, and transfers it to a comparatively tiny spacecraft. Jupiter, in the process of accelerating a passing probe, technically slows down by an amount so infinitesimally small that no instrument in existence could ever hope to measure the difference. While that same tiny transfer of momentum can add several kilometers per second to a spacecraft weighing a few thousand kilograms. It is, in effect, borrowing a fraction of a planet's own vast, ancient momentum, accumulated since the solar system's formation billions of years ago, and putting it to work for a single, comparatively brief human mission. The Cassini mission to Saturn leaned heavily on this technique, executing what's known as a Venus-Earth-Jupiter gravity assist trajectory, a carefully choreographed sequence of flybys past 4 separate worlds, spending nearly 7 years pinballing through the inner solar system, gradually, patiently building up enough velocity to finally reach the outer planets at all. An even more striking example is currently unfolding in real time. The joint European-Japanese Bepi-Colombo mission, launched in October of 2018, is flying one of the most intricate trajectories ever mapped by human engineers on its way to Mercury, the innermost planet of the solar system, and, counterintuitively, one of the hardest to actually enter orbit around. Because the Sun's gravity is so overwhelmingly dominant that close in, a spacecraft approaching Mercury directly would be accelerated to a speed far too great to safely settle into orbit. Instead, Bepi-Colombo has been threading an elaborate, multi-year path involving 1 flyby of Earth, 2 flybys of Venus, and a full 6 separate flybys of Mercury itself, each one bleeding off just a little more of the spacecraft's excess velocity, gradually, patiently, over the better part of a decade. Following a thruster anomaly discovered in 2024, the mission's final orbital insertion has been pushed back to November of 2026. Meaning that for the engineers who designed and built this spacecraft, a single mission has consumed a genuinely enormous portion of their entire professional careers, spanning roughly from conception to the edge of retirement, before the vehicle even reaches its intended destination. There's something worth sitting with in that. When we picture a mission to another planet, we tend to imagine it in terms of the mission itself: launch, journey, arrival, discovery. We rarely picture the human beings behind it, the engineers who designed a specific flyby sequence in their 30s, and might not see its final, successful outcome until they're approaching retirement, decades later. Interplanetary exploration, on this scale, isn't simply a technical challenge. It's an act of extraordinary institutional patience, requiring entire careers, sometimes entire generations of engineers, to hand a single mission carefully from one set of hands to the next, trusting that the mathematics laid down at the very beginning will still hold true, faithfully, a full decade or more later. Cassini's own story didn't end quietly, either. After nearly 13 years orbiting Saturn, having long since exhausted the fuel it would have needed for further maneuvers. Mission planners faced a genuinely difficult decision. Rather than simply leave the spacecraft drifting, uncontrolled, in Saturn's orbit indefinitely, with a small but real risk that it might eventually collide with one of Saturn's own moons, potentially contaminating a pristine, scientifically precious environment with residual Earth microbes still clinging to the spacecraft after 2 decades in space. Engineers chose deliberately to end the mission themselves. In September of 2017, they steered Cassini directly into Saturn's own atmosphere in a sequence known as the Grand Finale, transmitting scientific data for as long as physically possible before the spacecraft finally, deliberately burned up, ensuring that moons like Enceladus and Titan, worlds with real, live scientific interest in the possibility of their own biology, would remain uncontaminated for whatever future mission might eventually go looking there. Space, more than almost any other environment human engineering has ever attempted to operate within, demands something close to perfection. There is no roadside assistance, no repair shop, no possibility of pulling over to fix a mistake. And the history of interplanetary exploration is, honestly, a graveyard filled with brilliant, meticulously engineered machines, brought down not by dramatic cosmic catastrophe, but by small, almost forgivable human errors. A decimal point, a mismatched unit, a single second of corrupted data. Let's walk through a few of these stories slowly, because each one carries its own quiet, sobering lesson about exactly how thin the margins of interplanetary engineering truly are. In December of 1978, in a rare, almost accidental twist of good fortune, NASA dropped 4 separate probes into the crushing atmosphere of Venus as part of the Pioneer Venus mission. None of them designed with landing gear or parachutes or any expectation of surviving actual contact with the surface at all. They were built purely to gather data during their descent, expected to be destroyed the instant they struck the ground. One of them, nicknamed the Day probe, defied every expectation placed on it. It survived the impact, hitting the surface at a modest 35 kilometers per hour, and then, remarkably, kept functioning. Shrugging off 92 atmospheres of crushing pressure and 460 degrees of relentless heat, continuing to transmit genuinely valuable scientific data back to Earth for a full 67 minutes entirely by accident, having never once been designed to survive that long or at all. Then there are the failures, considerably more common, considerably more sobering. In September of 1999, the Mars Climate Orbiter approached the planet for what should have been a routine, carefully planned orbital insertion. It vanished behind Mars and was never heard from again. The subsequent investigation revealed a genuinely painful cause. One team of aerospace engineers had supplied critical thruster data using imperial units, pound force seconds, while NASA's own navigation software on the receiving end expected that same data in metric units, Newton seconds. Nobody caught the mismatch. The resulting trajectory error sent the spacecraft plunging 60 kilometers too deep into the Martian atmosphere, destroying the entire $125 million mission in an instant, over a unit's conversion that, on Earth, most of us would consider an easily correctable footnote. Just months later, in December of 1999, the Mars polar lander suffered its own catastrophic failure, entering the atmosphere on an entirely separate mission. As its landing legs deployed during descent, the ordinary mechanical jolt of that deployment sent a brief electrical signal through the spacecraft's systems, a completely normal, expected vibration. But the onboard software, lacking a proper way to distinguish that harmless mechanical jolt from a genuine touchdown signal, mistakenly interpreted the vibration as confirmation that the lander had already reached the Martian surface. Believing its job was finished, the computer shut off the descent engines entirely, while the lander was still hovering 40 meters above the ground. It fell the remaining distance at a devastating 22 meters per second, destroyed by a single misread signal at the very last moment of an otherwise successful descent. In December of 2003, the British-built Beagle 2 lander touched down on Mars and simply went silent, with no explanation for over a decade. High-resolution orbital imagery, captured years later, finally revealed the truth. The lander had, in fact, survived its descent perfectly. A genuine engineering triumph. But one of its solar panels, shaped like a folding petal, failed to unfold completely, leaving it stuck at an awkward angle. Because the spacecraft's communication antenna happened to sit directly beneath that one stubborn panel, the lander was permanently, physically silenced, sitting intact, functional, entirely alive in every sense that mattered on the Martian surface, with no way to ever tell anyone it had survived. And in October of 2016, the European Space Agency's Schiaparelli lander successfully deployed its supersonic parachute, executing what appeared, for a moment, to be a flawless descent. But the violent, natural oscillation of that parachute briefly overwhelmed the spacecraft's inertial measurement unit, its onboard sense of orientation and motion, for a single brief second. That 1 second of corrupted data fed directly into the navigation computer, which calculated, incorrectly, that the lander was already 1.8 kilometers below the actual Martian surface. Believing it had already landed, the computer immediately released its parachute and fired its braking rockets for a mere 3 seconds, instead of the full 30 seconds the descent genuinely required. The lander fell the remaining 3.7 kilometers to the surface, striking the ground at 540 kilometers per hour, an entire, otherwise successful mission, undone by a single second of bad data. None of these missions failed because the underlying engineering was sloppy, or because the teams behind them were careless. Quite the opposite. Every one of these spacecraft represented years of meticulous, world-class engineering brought down by margins so thin that even the most careful human teams, working with the best tools available at the time, occasionally couldn't catch them in advance. That is, perhaps, the single most sobering truth in all of interplanetary exploration. In the vacuum of space, there is no such thing as a small mistake. There is only success, or catastrophic, often silent, failure. And the gap between the two is sometimes no wider than a single unit of measurement or a single second of unfortunate timing. There's a particular kind of grief specific to this field, worth naming honestly. Unlike most engineering failures, which happen in view of the people trying to fix them, a spacecraft failure at Mars happens in total isolation, hundreds of millions of kilometers away, witnessed by no one, understood only afterward through painstaking forensic analysis of the last fragments of data the spacecraft managed to send home before falling silent. The Beagle 2 team spent over a decade not knowing whether their lander had even survived its descent at all, carrying that uncertainty, unresolved, for years, until an orbital camera finally, quietly settled the question, revealing a lander that had done everything right and simply run out of luck at the very last step. For 60 years, the same fundamental constraints. The punishing rocket equation, the razor-thin margins of autonomous landing, the crushing cost of lifting anything at all out of Earth's gravity well, shaped essentially every mission ever flown. Tonight, in the second half of the 2020s, several of those constraints are genuinely, measurably beginning to give way across 3 separate fronts at once. The first front is reusability. For most of spaceflight's history, multi-million-dollar rockets were used exactly once, and then discarded. Burned up on re-entry, or left to sink into the ocean, an entirely disposable machine, built at extraordinary cost for a single use. SpaceX's Falcon 9 broke that pattern first, successfully, repeatedly recovering its first stage booster, dramatically driving down the cost of reaching low Earth orbit to somewhere between roughly $1,500 and $7,000 per kilogram. Already a substantial improvement over the historical norm. But the more genuinely transformative shift is the Starship program. Standing a full 122 meters tall, Starship is, by any measure, the largest, most powerful flying vehicle ever constructed, purpose-built for complete, rapid reusability rather than the partial recovery earlier rockets managed. In October of 2024, SpaceX achieved something that would have sounded like science fiction only a few years earlier, catching the entire 71-meter super heavy booster out of mid-air using a pair of massive mechanical arms mounted directly on the launch tower itself, nicknamed, with characteristic informality, the chopsticks. Through 2025 and into 2026, subsequent test flights have continued expanding the vehicle's capabilities, demonstrating in-space engine relights and steadily increasing propellant capacity, with the ship itself now capable of carrying up to 1,500 tons of propellant in a single flight. Designed to eventually lift somewhere between 100 and 200 metric tons into orbit in a single launch, Starship functions less like a traditional rocket and more like an orbital cargo train, dramatically, fundamentally increasing the sheer mass humanity can realistically send toward the Moon, and eventually toward Mars. It's worth pausing on how genuinely radical that catch maneuver actually was from an engineering perspective. For the entire history of spaceflight up to that point, a returning rocket booster either splashed down in the ocean, landed on its own legs on solid ground, or was discarded entirely. Catching a 71-meter, multi-hundred-ton booster out of the sky, using mechanical arms precise enough to grab it without crushing it, moments after it had been traveling at hypersonic speed, represents a level of guidance precision that would have seemed almost fantastical to the engineers of the Apollo era, working with computers less powerful than a modern calculator. The second front is a concept called in situ resource utilization, living off the land, rather than hauling every single resource a mission might ever need across the entire journey from Earth. Between April of 2021 and August of 2023, a toaster-sized instrument aboard the Perseverance rover, named MOXIE, achieved something genuinely historic. Using a solid oxide device heated to 800 degrees Celsius, it extracted carbon dioxide directly from the thin Martian atmosphere and split it apart into carbon monoxide and pure molecular oxygen. Across 16 separate operational runs, MOXIE produced a total of 122 grams of breathable, 98% pure oxygen, roughly enough to sustain a small dog's breathing for about 10 hours. The quantity itself was modest. What it proved was not. For the first time in human history, a machine on another world manufactured its own breathable air and demonstrated a viable path toward producing liquid oxygen for rocket fuel as well. Fuel that could, eventually, power a return journey home without ever needing to be carried there in the first place. Beyond air and fuel, mission planners looking toward the late 2020s and into the 2030s are increasingly relying on robotic three-dimensional printing systems designed to gather local regolith directly from a planetary surface, mix it with binding agents or melt it using concentrated solar heat, and extrude it into thick, naturally radiation-resistant habitat walls, building genuine shelter out of the very ground astronauts would be standing on, rather than shipping heavy prefabricated structures across the abyss between worlds. It's a concept worth holding in your mind alongside a simple, grounding comparison. In situ resource utilization is the difference between a wilderness explorer hauling 100 gallons of bottled water and a prefabricated brick house on their own back, versus that same explorer carrying only a lightweight water filter and the knowledge of how to build shelter from whatever materials the land itself already provides. And the third front, still very much in active development, is nuclear propulsion. The technology most likely, over the coming decade, to finally meaningfully shorten the punishing travel times that have shaped every mission discussed tonight. Chemical rockets are, by this point, approaching the practical limits of their own efficiency. Reducing the roughly 9-month transit time to Mars, and correspondingly reducing astronaut radiation exposure along the way, genuinely requires a different category of propulsion entirely. Two main approaches are under active development: nuclear thermal propulsion, where a compact fission reactor superheats liquid hydrogen and expels it through a nozzle at roughly double the efficiency of chemical engines, and nuclear electric propulsion, where a reactor instead generates electricity to power highly efficient ion or plasma thrusters, providing gentle, continuous acceleration sustained across the entire journey, rather than one brief, violent burn followed by months of silent coasting. Early in the 2020s, NASA and the Defense Advanced Research Projects Agency collaborated on a nuclear thermal demonstration program called DRACO, aiming to test an actual reactor in orbit by 2027. But as SpaceX's Starship program made delivering enormous quantities of ordinary chemical propellant into orbit dramatically cheaper than anyone had previously assumed possible, the substantial research costs of DRACO became progressively harder to justify, and in May of 2025, the program was formally cancelled, its research quietly folded back into NASA's broader technology portfolio. That setback didn't end the momentum toward nuclear propulsion. It simply redirected it. In March of 2026, NASA unveiled a new concept called Space Reactor 1 Freedom, an ambitious proposal aiming for a 2028 demonstration launch of genuine deep space nuclear electric propulsion built around high-assay, low-enriched uranium fuel. Around the very same time, engineers at NASA's Jet Propulsion Laboratory successfully tested a prototype lithium-fueled plasma thruster, achieving 120 kilowatts of continuous power output, roughly 25 times more powerful than the electric thrusters currently flying on any operational spacecraft. Taken together, a megalift reusable rocket capable of hauling enormous mass into orbit affordably, resource extraction technology capable of manufacturing air and fuel on arrival, and a genuinely new generation of nuclear propulsion capable of cutting travel time dramatically. Mission planners now speak with real, grounded confidence of eventually reducing the Mars transit from 9 grueling months down to a far more survivable 3 to 4 months. It would be, without exaggeration, one of the single largest reductions in interplanetary travel time in the entire history of spaceflight, made possible not by any single breakthrough, but by 3 separate, hard-won technological revolutions converging together in this exact decade. Let's sit with everything we've walked through tonight and ask what it actually adds up to. Every single obstacle covered tonight. The impossibility of a straight line, the punishing tyranny of the rocket equation, the crushing pressure of Venus, the paper-thin margin of Mars's atmosphere, the invisible radiation quietly flipping bits inside a spacecraft's own memory, the abrasive dust, the violent thermal swings, the unbridgeable delay of light itself. Exists because the solar system was never built with anything like us in mind. Every planet, every stretch of empty space between them, every physical law governing how fast something can travel or how much fuel it takes to get there, formed billions of years before life existed anywhere to care about any of it. And into that entirely indifferent environment, human beings have spent the last 7 decades deliberately, repeatedly, sending some of our most careful, most meticulous engineering. Machines built by teams who understood, going in, exactly how narrow the margin for error would be, and chose to attempt the journey anyway. There's something worth noticing in the sheer persistence of this effort, especially set against the graveyard of failures we spent real time with a few chapters ago. Every single one of those failed missions, the unit's mismatch, the misread mechanical jolt, the single corrupted second of navigation data, could easily have discouraged an entire generation of engineers from trying again. None of them did. Each failure was investigated, understood, and folded directly into the design of the next mission, and the one after that, in an unbroken chain of hard-won lessons stretching back to the earliest days of interplanetary exploration. The 7 minutes of terror sequence that now reliably, repeatedly lands 1-ton rovers safely on the Martian surface exists specifically because earlier missions failed, and because engineers refused to treat those failures as a reason to stop. This is, in its own quiet way, one of the more remarkable expressions of a distinctly human trait. Not simply curiosity, though curiosity is certainly part of it, but a specific, disciplined willingness to fail precisely, learn exactly what went wrong, and try again with genuinely improved odds. The margin for error in interplanetary engineering will likely never disappear entirely, but it has narrowed, mission after mission, decade after decade, through nothing more dramatic than careful people, refusing to let a single misplaced decimal point be the end of the story. There's a broader pattern worth noticing here, one that connects the rocket equation, the 7 minutes of terror, and the graveyard of failures into a single, coherent story. At every single stage of tonight's journey, the solar system offered no shortcuts, no forgiveness, no partial credit for good intentions. And at every single stage, human engineers responded not by demanding the universe be gentler, but by getting more precise, building triple redundant computers to outsmart cosmic radiation, designing thermal systems that could survive impossible swings in temperature, writing autonomous software capable of making split-second decisions no human hand could ever reach in time to help with. The universe never once lowered its standards. We simply, patiently, kept raising our own. Consider, too, the quiet economics behind all of this persistence. Every mission discussed tonight, the successes and the failures alike, cost hundreds of millions, sometimes billions, of dollars, and consumed years, sometimes entire decades, of specialized human labor. None of that investment was recoverable in any ordinary sense if a mission failed. There was no salvage, no partial return, no way to recover so much as a single bolt from a spacecraft destroyed 100 million kilometers away. And yet space agencies, private companies, and entire nations have continued making that investment, mission after mission, generation after generation, driven by something that resists easy economic justification. A stubborn, deeply held conviction that understanding what lies beyond our own planet is worth the staggering cost of trying, even when trying so often ends in silence. Here, finally, is the thought I want to leave you with tonight. Everything covered in this documentary, the merry-go-round physics of orbital mechanics, the exponential tyranny of the rocket equation, the crushing furnace of Venus, the paper-thin atmosphere of Mars, the invisible radiation silently testing every circuit in every spacecraft we've ever built, exists because we chose, as a species, to leave the one environment we were actually built for and go, looking deliberately for somewhere else. Every cell in your body, every reflex, every intuition about movement and gravity and temperature was shaped by hundreds of millions of years of evolution unfolding entirely on the surface of one comfortable, temperate, gravity-bound planet. Nothing in that long evolutionary history ever needed to account for a 9-month coast through the vacuum, or a 7-minute, fully autonomous plunge through an alien atmosphere, or a communication delay long enough to make real-time conversation physically impossible. And yet, here we are, tonight, sending machines, extensions, in a very real sense, of our own curiosity, into precisely the kind of environment our own bodies were never designed to survive, on our own terms, entirely on the machine's behalf. There's a particular kind of meaning worth sitting with in that. We are not the fastest creatures. We are not the strongest, or the most naturally suited to hostile environments. What we have, instead, is something considerably rarer. The capacity to look honestly at an environment that wants nothing more than to destroy anything we send into it, catalogue exactly how and why, and then spend decades, sometimes entire careers, quietly, patiently engineering around every single obstacle, one narrow margin at a time. Consider what it actually means that a piece of software, running on a rover 100 million kilometers from the nearest human being, makes a genuinely independent decision to fire its retro rockets, or lower itself on cables, or swerve away from a hazard, entirely on its own, because we built it carefully enough to trust it with exactly that responsibility. That trust, placed in machines we'll never be able to speak with in real time, sent to places we ourselves have never stood, is its own quiet, remarkable act of faith. Not faith in something beyond understanding, but faith earned the hard way, through failure after failure, each one folded carefully into the next design until the odds of survival crept, slowly, meaningfully upward. There's an image worth holding on to here, drawn directly from tonight's story. A radioisotope generator, powered by plutonium with a half-life of nearly 88 years, will keep quietly producing heat and electricity for a Mars rover decades after the mission that sent it has ended. Decades after the engineers who built it have retired, quite possibly decades after some of those engineers have passed away entirely. That rover will still be sitting there, warmed by a small, patient, radioactive heart, long after everyone who understood exactly how it worked is gone. There is something almost tender in that. A piece of engineering built to outlast its own creators, carrying their careful, hard-won knowledge forward across a stretch of time none of them will personally witness. And consider, too, what it means that we keep going. Even now, even after Mars Climate Orbiter, even after Mars Polar Lander, even after Beagle 2's silent, intact, forever unreachable landing. Every one of those failures could have been read as a message to stop reaching outward, to accept the comfortable boundaries of our own planet and stay. Instead, each failure became a lesson, folded carefully into the next attempt, narrowing the margin for error just a little further, mission after mission, decade after decade. That refusal to be discouraged by an indifferent, unforgiving universe may be one of the truest expressions of what it means to be a curious, mortal, endlessly persistent form of matter, built from stardust, reaching back out toward the stars that made it. So let's gather up everything we've walked through together tonight, gently, before we close. We began by dismantling the comforting illusion of easy space travel, discovering that nothing in the solar system holds still long enough to simply be aimed at directly. We sat with the punishing mathematics of the rocket equation and watched the largest rocket ever built deliver less than 2% of its own weight as useful cargo. We walked through two opposite planetary traps. Venus, crushing and furnace hot, and Mars, thin-aired and merciless in an entirely different way, and followed a rover through its own 7 minutes of terror, entirely alone, entirely autonomous, hundreds of millions of kilometers from the nearest human hand. We met the invisible enemies waiting on every surface. Cosmic radiation flipping bits inside a spacecraft's memory, abrasive dust grinding away at seals, and temperature swings severe enough to crack steel. We confronted the unbridgeable delay of light-speed communication, followed decades-long trajectories built around stolen gravitational momentum, and revisited some of the most heartbreaking failures in the history of interplanetary exploration. Each one a reminder of just how little room for error this environment allows. And we ended by looking toward the genuine, hard-won technological revolution now underway. Reusable rockets, homemade oxygen on Mars, and a new generation of nuclear propulsion, slowly, patiently narrowing the gap between what's possible and what's merely imagined. No dramatic, tidy ending tonight. Just an honest, careful accounting of exactly how hostile this journey has always been, and exactly how much patient, hard-won engineering it has taken, and will continue to take, to make it survivable at all. And there is something worth carrying with you into sleep from a story built entirely around distance, patience, and the slow, careful triumph of engineering over an indifferent universe. Tonight, wherever you are resting on the one world in this entire solar system that never demanded any of this from you. A planet with a breathable atmosphere, a gentle, forgiving temperature, and a magnetic field quietly shielding you from the very radiation that spacecraft engineers spend entire careers designing around. You don't need a heat shield tonight. You don't need a radiation-hardened processor, or a 7-minute autonomous landing sequence, or a nuclear battery keeping you warm through the dark. Every comfort spacecraft engineers spend years trying to recreate artificially somewhere else is already, quietly, freely provided for you, right where you're lying. There is a particular kind of rest available in a story this thoroughly grounded in patience. So much of what keeps a mind restless at the end of a long day involves things that feel urgent, unfinished, demanding a decision before sleep will come. Nothing in tonight's story asks that of you. The trajectory calculations happening right now, for missions still years away from launch, will keep unfolding at exactly their own careful pace, whether you're awake to think about them or not. The rover sitting patiently on the Martian surface will still be there tomorrow, warmed by the same quiet plutonium heart, waiting out the same long, cold Martian night, entirely independent of anything happening in the room where you're lying right now. Let that be enough for tonight. Somewhere right now, a rover is sitting quietly on the cold Martian surface, its plutonium heart glowing faintly with warmth it will keep generating for years to come, entirely alone, entirely patient, waiting for the Martian sun to rise again. You can rest exactly the same way. Patient, warm, and, unlike every machine we sent searching on our behalf, held gently by a planet that has never once tried to destroy you. Good night. Sleep well. And if tonight's journey gave you a little more to wonder about, consider liking this video or subscribing to the channel. It helps this kind of slow, patient storytelling find the people who need it. Thank you for spending these hours with me tonight. Good night, and sleep well, held by the one world in the solar system that was always, quietly, on your side.